Hello there. Welcome to AMPP Corrosion 2021. This is paper 16368. My name is Colin Scott. I'm an independent pipeline integrity engineer. I'm working out of Calgary, Alberta, up in Canada. Today I'm going to talk to you about a statistical analysis of the gamma exponent model. And the gamma exponent model, or the GEM, is something that I've been developing for the last couple of years. And it's a flaw assessment model that can look after both corrosion and cracking. So it's got some universal applicability. And this is all part of my my sort of unofficial global campaign to rid the world of ASME B31G. That model and I, we really don't see eye to eye. Now, B31G is an equation that we all kind of sort of take for granted, right? It's been around for 50 years. We use it for corrosion assessments. Nobody really stops to, take a closer look at it. I have taken a closer look at it, and I'm not a fan. Now, the model it's empirical. Right? So there's no formal derivation behind B31G. It's somebody sort of put some math together and it kind of sort of seemed to work, and so nobody really thought twice. But if you stop and think about it, the B31G equation is built around the Foley's factor. And the Foley's factor is a length factor that was originally formally derived for through-wall crack assessment. The question there was, if you have a short leaking flaw, will it get longer and rupture? But for some reason, we're using this length-based through-wall cracking equation to somehow assess surface flaws. But with surface flaws, length really doesn't matter, right? The depth matters. We're not worried about a short crack getting longer. We're worried about a shallow crack or shallow corrosion flaw getting deeper. So to have the Foley's factor in there is kind of, quite frankly, nonsensical. And what it does is it mathematically focuses the failure strength predictions far too much on length, and that makes all the math go completely wonky. My estimate is that the wonky math is probably costing the industry around $3 billion, maybe $5 billion a year in completely unnecessary repair costs. So I'm trying to fix that and just be a bit more sensible about how we do our math. I have a former professor who said you really don't need an outline in a presentation, just start at the start, end at the end, so I'm just going to keep moving here. Now, here's my gamma exponent model, and those of you in the cracking business will notice that it's very, very similar to the original log secant model that's used for surface crack analysis. Now, if we look back 50 years ago, somebody came up with a log secant model for through-wall cracks, and that's a really good model. And then they took that model and they took the B31G equation and they kind of like Frankensteined it together, and they thought, well, now we have a log secant model for surface cracks. Isn't that wonderful? But really, mathematically, not so much. So what I decided to do is to redo the log secant model derivation, but rather than starting with a through-wall crack, going through all the math, and then empirically correcting for depth, I decided let's do it the other way around. Let's assume that we're starting off with a part through-wall crack, assume it's infinitely long, go through all the log secant model math, and then at the end of it empirically correct the length. That way you're mathematically focused on depth rather than on length. Length kind of doesn't matter. Now what's really interesting with this is when I do the log secant model derivation for a part through-wall crack, I actually I have to put in a backwall correction factor, which in this case is the square root of the secant of the flaw depth. And what's really cool about this equation is if I put in that secant term and I go through all the mathematics, at the very end, I pop out with this remaining ligament to the gamma exponent term, which kind of sort of replaces the need to Frankenstein in a B31G equation. So you look at the equation, I've got a remaining strength, the predicted failure strength over the flow strength. I've got a remaining ligament term to the gamma exponent, pi over 2, and then I've got an arc cos exponential term, which looks quite similar to the log secant model, except that it's based on depth. It's not based on length. Okay. Now, very similar to the log secant model for surface cracks, I sort of have a flow strength kind of term, and then I use that just for corrosion, and then I also have a flow strength and fracture toughness terms, which I use for the stress corrosion cracking. So it's kind of analogous to that log secant model for surface cracks, but there's some key differences. I mean, it's based on depth, not on length, so that's key. Now, the small print here is if I'm doing a corrosion assessment, I'm not going to use the whole equation. I just use that flow strength equation. What I'll do for corrosion is I will assume that I've got a kind of sort of a semi-elliptical flaw profile, and I'll multiply the flaw depth ratio by a pi over 4 factor. That's a pretty common thing that we do in the fracture mechanics business. If I do have a full profile, I use my effective length method, which I'm going to show you a little bit later on. And then here you'll see that I've got the gamma exponent defined as the length of the flaw divided by the radius of the pipe up to a maximum of 1/2. And that's kind of important, and it's going to have some of you scratching your heads. The first thing is it basically means that we're not looking at any length of corrosion that's more than 1/4 of the diameter. If your flaw is 1/4 of a diameter or the length of the football field, mathematically, it really doesn't affect your failure strength prediction. I know that's going to surprise you, but it kind of works out that way. And the second thing, and this is going to have various people sort of, stopping the video right now and sending letters to the editor, is that maximum gamma exponent of 1/2 means that if I have a long flaw, then my failure strength is proportional to the square root of the remaining ligament. That's actually going to explode a few people's heads. The failure strength is not proportional to the remaining ligament. It's proportional to the square root of the remaining ligament. And before you get too upset about that, there actually is a technical rationale. That number is theoretically derived when I go through the formal derivation. You can find that in ASME Journal of Pressure Vessel Technology. So try and hold off on the letters for a little bit. Now, if I'm using stress corrosion cracking, I'm going to use both the flow strength term and the fracture toughness term. I'll do the same thing with the pi over 4 factor. But then I also include a crack shielding factor. Yeah, people talk about crack shielding and stress corrosion cracking, but I am yet to see anybody that's actually tried to include some sort of correction factor into their failure pressure models. And that becomes very, very important because if you have multiple cracks that are all near each other, they actually end up shielding each other's stress intensities. The stress intensity gets shared amongst all the cracks. And when you look at the math, which we'll look at later on, from a stress intensity factor perspective, there's a decrease of about 10% to 30%. And then when you sort of square those numbers and do a J integral calculation, you're changing by about 20% to 50% lower. So that's actually quite significant. And I'll kind of walk you through how we do that. It's kind of interesting. In the case of a crack, I do not limit the gamma exponent to 1/2. It goes to the 1, so that should make some of you feel quite a bit better. So let's take a look at how this all plays out. I do have some industry failure data. Cronin data and Battelle data is all corrosion stuff. The Rothwell data and the Davies data is stress corrosion cracking stuff. I find it very difficult to find stress corrosion cracking data. The papers will mention them sometimes, but the data is not necessarily publicly available. I think that there's some people that are worried that somebody like me might get their hands on some data and actually develop a new flaw assessment methodology that might save them, I don't know, tens or hundreds of millions of dollars, and we wouldn't want that, would we? Okay, so here's my corrosion data. It's not actually a Jackson Pollock painting, which it kind of looks like from a distance. On the y-axis, we have the predicted failure strength using either the gamma exponent model, which I just mentioned, or using modified B31G. On the x-axis, we have the true failure strength, which is measured in a laboratory hydro test. And you'll see here that, quite frankly, neither model is particularly good. We've got 2 overlapping shotgun blasts. You'll see just from this level 1 analysis that the GEM model is slightly more accurate than the modified B31G, but nobody's really having any parties over this validation, quite frankly. They're both kind of messy. Now, one thing that I will point to is notice that there are some non-conservative predictions here. And this is a level 1 assessment, and there are some non-conservative predictions. Those are the ones that are over the unity line. We've got most of our data points below the unity line, which means that they are conservative, which is safe for our pipeline, but potentially very expensive if you're the pipeline operator that's paying the bills on doing the repairs. So let's see if we can improve on that. I think we can. Now, some of you will be familiar with the R-string model, and with the R-string model, what you do is you actually look at every length and depth combination from one end of the flaw to the other end of the flaw. And for each one of those length and depth combinations, you'll calculate the area of, the area of the corrosion flaw. And you'll divide that area by the length, and you'll come up with an average depth. And then you'll take that length and average depth, you'll put it in the basic B31G. You'll do that for every combination and permutation from here until the end of time. And then you'll choose the lower bound, right? And of course, that includes a full use factor, which I kind of sort of don't agree with, as I mentioned before. Now, what I do with the GEM, my effective length method, is I flip things around a little bit. I don't look at every length combination. I only look at 1/4 diameter, because that's the mathematical limit of where my gamma exponent is going to be. And then rather than dividing by the full length and getting an average depth, I take the area under the curve and I divide it by the local maximum depth in order to get an effective length. And then I will take a look at, every 1/4 diameter length from one end of the flaw to the other, do the calculation, choose the lower bound, right? Couple key differences there. And then, of course, I've got the square root in there that is going to drive some of you completely crazy. Let's see how that plays out. Okay, so here we can see that the GEM, the effective length method, my level 2 assessment, has taken all of those green diamonds and it's basically condensed them right along the unity line. It's actually 1% off, but it's pretty darn close. So that means that I've got some confidence that the mathematics behind this model is pretty darn good. If I look at the R-strain calculations, and these are R-strain calculations that were in the Cronin report. I should mention that all the profiles that I had, they were Cronin. Battelle didn't have any profiles for me to play with, so this is a limited subset. You'll see that the R-string data, they've all condensed along a line, but it's a conservative line. And that's a kind of important thing, and we'll get to the statistics a little bit later. But one thing I want to mention is we saw before with the level 1 analysis, there were some non-conservative predictions. When we go to a level 2 assessment, now everything is conservative, which is kind of sort of backwards from our typical assessments, right? Usually, when you're doing an assessment, you assume that level 1, basically your lazy assessment, is going to be conservative, and if that works, you're fine. But then if that doesn't work, then you would go to a level 2 assessment, which is more detailed, which kind of sort of should be less conservative, right? But in this case, for both models, both GEM and B31G, there is a certain series of level 1 predictions that are non-conservative. And when you go to the level 2, you become more conservative, which is kind of sort of backwards. That's something to think about. If you dig into the mathematics, you'll find that those non-conservative mod B31G predictions, they tend to be the shorter flaws, and the overly conservative predictions tend to be the longer flaws. And that's actually kind of an interesting thing because it brings up a catch-22 situation for the various pipeline operators. If they find a long flaw, they're going to run through the math, they're going to find a really low failure pressure, low predicted failure pressure, and they're going to run out and dig that flaw. But based on the conservatism in this model, those longer flaws actually have a higher degree of conservatism, meaning that you probably don't need to dig them. Kind of a catch-22 situation, but... I should also remind everybody that with this GEM, all these diamonds that are magically lining up along the diagonal, remember, square root relationship. So think about that for your letter to the editor. Okay, I think we're done with corrosion for now. We're going to jump into stress corrosion cracking for a couple of minutes. Now, if you find your crack analysis handbook from Tata, Paris, and Irwin, you'll find that there's a stress intensity factor solution for what they call periodic crack arrays. So that basically means you've got lots of cracks kind of lined up parallel to each other, just like you would find in a stress corrosion cracking colony, right? They're all parallel. Now, the effect of this is, as I mentioned before, you get this crack shielding effect, where if the cracks are close enough together, they start to influence each other's stress intensity, and they kind of share that stress intensity, decreasing the overall, which is good, right? It's actually, as contradictory as it sounds, that's actually safer for the pipe, right? Now, if you look at the stress intensity factor solutions, you'll find that these crack arrays, they become thermodynamically metastable when the crack's depth to spacing ratio is 1/3, which sounds a little weird. That means that as your cracks grow, they're going to get to a point where they start to influence each other enough that they kind of cancel out each other's stress intensity factors, and they actually go dormant. Yeah. So the dormancy that we sometimes talk about in stress corrosion cracking, can potentially be explained using thermodynamics as opposed to various electrochemistry answers that some people have come up with. Now, there's a very interesting paper out there by a fellow named Parker, Anthony Parker. He was doing some research work at one of the military colleges in England. And what he demonstrated, which is fascinating, is the cracks will grow until they have spacing of 1/3, and then they'll go dormant. But he came up with, he recognized that there was a phenomenon that he called shedding, where 2/3 of those cracks will go dormant, but then 1/3 of the cracks, equally spaced, will remain live, and they'll continue to grow. Yeah, and they'll continue to grow with a new spacing ratio until they also reach 1/3. And what this means is that you get this crack and shed sequence where the live cracks are alternating between a 1-in-3 spacing and a 1-in-9 spacing, and they kind of flip-flop back and forth as the live cracks grow. And what I've done is I've used that phenomenon to come up with an effective depth factor. And I've thrown that into my stress corrosion cracking model. Now, when I mention this sort of 1/3, 1/9 kind of crack depth spacing ratio, it kind of sort of doesn't make a whole lot of sense until you dig up your old American Gas Association Pipeline Research Council study from 1974, and you find this quite beautiful metallographic cross-section. Now, what's interesting is if you look at the cracks, their spacing is approximately equal. And what you'll also notice is that the crack depths are either equal to that spacing or 1/3 of that spacing, other than the failed one right in the middle. I've done a little color coding to hopefully help you understand this a bit. Yeah, so here I've come up with sort of an arbitrary color code where I say, consider that red is a dimension of 1, consider that green is a dimension of 3, and consider that blue is a dimension of 9. And when you look at the spacing of all of these, primary cracks, I'll call them, is 3. We have some of the deeper cracks are 3, except for the one that went through wall. And then the intermediate cracks, these have a dimension of 1. So you get this 1-in-3 spacing and this 1-in-9 spacing, which is basically gives us confidence that Parker was really onto something. I strongly recommend reading his paper. It's not an easy read, but once you kind of wrap your head around it, it's pretty amazing, and it kind of sort of seems to work. This isn't perfect, but when you consider this is a natural phenomenon, and we see this 1-in-3 spacing, blows my mind. So what I did with the Tata Paris-Irwin stress intensity factors and compliance factors is I kind of back calculated what's an effective depth to use in the GEM model. And because we've got a crack and shed sequence that's alternating between a 3rd and a 9th, I kind of used 2 different depth factors, and then I averaged them. Now, when I take my data and I plot it, I find a couple interesting things here. I only have 1 service failure, and if I use the average, that turns out to be non-conservative. But if I were to use the conservative value, it would be quite close to the correct true value. And what that makes me think is, if you have some cracks in a crack and shed sequence, if you have a service failure, it's very likely that that crack happened to be in the worst case scenario of its crack and shed sequence. So my suggestion at this point is to use the more conservative values for service failures. But for a hydro test, at any given time, you don't know where those cracks are in the crack and shed sequence, right? So I've sort of come up with a range, and the average and the range kind of sort of seem to work. Now, I've only got 9 data points, but I think this is working out pretty good. I'm pretty happy with it so far. Now, I guess I'm kind of probably getting to the end of my time slot. So I'll just say that I've shown you a few validation efforts. I've looked at level 1 and level 2 corrosion assessments, and I've got a level 1 SCC assessment. And if you compare those to the industry numbers, you'll find that it's really pretty good. Now, one thing I would like to point out and give you something to think about is there's a study put out about this time last year by PRCI. They were looking at R-streng and the p-squared model. And what they did is they reported the R-streng model has an average error of 30% plus or minus 10%. So what that means is the average error is 3 full standard deviations away from reality. Now, if this was a manufacturing process, we would say that we had like lost process control, right? 3 full standard deviations. If you think about your bell curve and the little tail on the bell curve, 3 full standard deviations corresponds to something like 0.2%. Now, there was a big improvement on going from R strength to P squared, but they still have an average error of 13% with a plus or minus of 7%. So that's almost 2 full standard deviations, and that little tail on your distribution is about 3%. Now, the proponents of this model, B31G in general, of which I am obviously not one of them, will tell you that those statistics demonstrate that R strength is conservative and P squared is conservative, and they can say that with a certain degree of statistical confidence. But I will let you know that the statistical confidence on the conservatism is actually a double-edged sword. Because if you look at the flip side, that means you have an equal lack of statistical confidence in the model being mathematically correct. The more sure you are that you're conservative means the more sure that your mathematics is not accurate and it's wrong. So think about that. It's a very important thing to think about because we're using this B31G model for mod B31G, for R strength, for P squared. It's being used in DNVF 101. It's being used in API 579, chapter 4 or 5 or whatever for corrosion. The same mathematics is also being used in all of our cracking assessments. It's in the log secant model for surface cracks. It's in Corlas. It's in PRCI's MAT 8 model. It's in British Standard 7910. It's in API 579, chapter 9. Pretty much every one of the flaw assessments that we're doing in the industry today is somehow based on B31G. And as the PRCI statistics show, it statistically, mathematically proves itself, disproves itself, proves that it doesn't work. And I think that we all need to have a good hard think about that because that is costing certain people tens or hundreds of millions of dollars. And the fact that we have bad math that's buried in everything we're doing, quite frankly, scares the heck out of me. I really think that everybody should take a serious look at this. So that's about it for me. Thank you for your time. If you've lasted this long, I appreciate it. If you have any questions, please, you can contact me through LinkedIn. I'm glad to answer questions about this. And anybody that wants to see what else is down the rabbit hole with regards to this, with regards to model development and the various mathematical issues I have with B31G, feel free to bounce onto my YouTube channel. I've got several videos just like this one where I explain what I think the mathematical issues are that we're dealing with, why we're dealing with them, and how to fix them. And I'm hoping that we can all kind of start the discussion that rids the world of B31G. So enough for me. Hope you're enjoying the conference. Thanks for your time.